Okay, so this session is about balancing of rotating masses. First, we consider balancing of rotating masses in a single plane, just one plane. We consider a shaft which is rotating in the anticlockwise direction with the speed omega, angular speed omega. Suppose there are two masses m1 and m2, and this angle is theta 1 with horizontal, and this angle is theta 2 with horizontal. So theta 1 and theta 2 are angles measured in counterclockwise direction from horizontal. This this is how angle is measured. Draw a horizontal line towards right and take in the anti-clockwise direction. That's how angle is measured. The radius is r1 and here the radius is r2. We know that when some object is rotating, it will experience centrifugal force, which is radially outward direction, Fc or Fc1. So Fc1 is the centrifugal force due to mass m1 and Fc2 is the centrifugal force due to mass m2. We know this equation Fc is equal to mv square by r. This v is r omega, so it is mr square omega square by r. That is mr omega square. So mr omega square Newton. That much Newton will be the magnitude of force, centrifugal force experienced by the mass m1. And how is the direction? Direction is always radially outward. Radially outward. Now, if you draw the vector diagram corresponding to these forces, first you can draw the vector corresponding to Fc1. According to take a suitable scale and mark Fc1. This angle should be same as theta 1. This Fc1 is m1 r1 omega square. And the next vector is Fc2. This is m2 r2 omega square. Now you can see that these two vectors are not balanced. So this is the resultant force. So the shaft will experience a resultant force of magnitude this one and along this direction. Okay. So the problem with this is the shaft will be subjected to uh, vibrations if the force is not balanced. Okay. And if we increase the speed, there will be increase in the centrifugal force because it move. If we double the value of omega, there will be 4 times increase in the centrifugal force because it increases the square of the speed. Okay, so for the machinery like turbines or such protective machinery, where the value of omega is very high, centrifugal force will be always very high. So in such cases, a very small amount of unbalance will cause severe damage to the system. Even the shaft may collapse. Okay, so that is the problem with unbalance. Now, how can we minimize the, or how can we neglect this resultant or cancel this resultant? To cancel the resultant, you have to add another mass which can produce the same centrifugal force in the opposite direction. So if you add another mass here, and this Fc3, if Fc3 is same as this resultant, then again if you draw the force polygon, Now you can see that F sigma F will be equal to 0 I. Now this is balanced. Okay. So this vector represents the force due to this balancing mass, and we may represent this as MB, and suppose the radius is RB. Okay. So this is how we balance the centrifugal force. Okay. So this FC3 should be equal to MB RB omega square. Okay, this is about a balance. Now, if you consider masses in different planes, multi-plane. So, if you consider multi-plane, means there are more than one plane in which mass is attached. There is one plane, say plane A, and some other plane, plane B, a third plane. Where so MA, MB, MC. Okay. So here also you can draw the force polygon. As in the previous case, first vector FC1, then second vector FC2, and third vector. Suppose it is like 1, 2, 3, or say A, B, C. It can be balanced. Okay. Okay. So this is a force polygon. If it is closed force polygon means there is no negative force. If it is closed one, negative force is 0. So it is balanced with respect to force. Now, if there are many planes which are separated by distance, suppose this is L1 and this is L2. Even if the force is balanced, it is not a sufficient condition for equilibrium. It may happen that the force is balanced, but the moment may not be balanced. So let us check the moment. Say take A as reference plane. A as reference plane. Now with respect to A, first you measure the distance between A and B. It is L1. So the force coupled due to B is CB. Coupled due to B or MB is CB, which is equal to MB RB omega square L1. This is coupled due to B. Then coupled due to CC is MC RC omega square L1 plus L2. L1 plus L2. Okay. What is coupled due to A? Coupled due to A is 0. Because this is taken as reference plane. So if you take a reference plane, then the moment of forces in that plane will be 0. So moment due to MA will be 0. Now with respect to A, we can draw the moment diagram. These vectors M1 or MC1 or MA and MB and MC. MB and MC. So Suppose this is moment due to B, and next this is moment due to C. Moment due to C. You can see that this is not closed. So there will be a resultant moment. Resultant moment. This is the resultant moment. Resultant moment. So we can see that in this case it is balanced with respect to force, but it is not balanced with respect to moment. So we can simply say that the system is not balanced. This is an unbalanced system. Unbalanced. Okay. So the point here is, in the case of single plane only force must be balanced. Only force must be balanced. And that kind of balancing is called static balancing. Static. But if you take multi-plane, more than one plane, multi-plane, both force and moment. Both force and moment should be balanced. And this is the case of multi-plane balancing. And that balancing is called dynamic balancing. So dynamic balancing is applicable for multi-plane. Okay, this is the basic. Now we will solve different problems then.